Okay, so what did we do in the previous class? We understood about the angular velocity, right? So let's say we had this body, or let's say if we are talking about a particle. So first we talk about a particle, and this was moving, and this was the point of observation, and this was the position vector, right? And this is tangential was this linear velocity. This was r, and perpendicular was this angular velocity. So this angular velocity, we calculated this was omega cross r, right? And this is the perpendicular distance, r perpendicular. So this v is omega r perpendicular. Let's say this r. Okay. So this we and then we proved that the angular velocity is d theta by dt. So this was the instantaneous angular velocity. And then we calculated the angular acceleration, which was d omega by dt. And then we talked about the torque, right? So this was the rotational analog of force, and this was r cross f, which is r perpendicular into m, right? So this was r perpendicular was r sine theta, right? So this we saw in the previous class, and then we saw the angular momentum, which was so this was r cross p, where this p was the momentum. So this is the rotational analog of the momentum, linear momentum, and this was the angular momentum. And then we saw the two conditions of equilibrium. So we talked about the equilibrium of rigid body. And there were two kinds of equilibrium, right? Because from this we got that the external force, external angular force, this was dl by dt, as what we got for the case of the linear one. For the linear one, this was F external was dp by dt. So for the case of rotational one, this one was the rotational analog, right? So for the case of equilibrium of rigid body, we saw two cases. One was the translation equilibrium. In this case, F external was 0, right? And then if the body is in equilibrium, then this would have also the rotational, right? And this is tau external to 0. So these are the two conditions that we saw. Whenever the rigid body is at equilibrium, so that will happen only if both the conditions are found. So that is that have the translation equilibrium as well as the rotational. But some of the bodies can have partial equilibrium, right? So we saw that there is this partial equilibrium also. And the case of the partial equilibrium was that we have only translational equilibrium, or we can have only the rotational. So whenever we have, let's say the two cases where, let's say this was the first case that we talked about. So this is a rod, and two forces, equal forces are acting in this direction. right? So this is F, magnitudes are same, right? Magnitudes are same and this is the center, right? So can you guys tell me what kind of equilibrium is that? What kind of equilibrium is this?
Translation.
Translation. So in translation, whatever is the upward force, that would be equal to the downward force. So do we have that condition?
So it won't be equal to zero. It is
Yeah,
rotational equilibrium.
yeah, rotational equilibrium. Because this one is going anti-clockwise and this one is going clockwise. So we have a rotational equilibrium, right? This is an example of rotation, right? But we see that F1 plus F2, so F plus F is not it, right? Or if I calculate F external, so F external would be F plus F, which is 2F. So that is not equal to 0. So this is the example of only rotational equilibrium, right? And we saw this example that we have, so we have this force which is going downward, right? Which means that we have a rotation in this way, and this force which is going upward with the same magnitude, right? So what kind of equilibrium is this?
Translational.
So this is only translation, right? So only translational equilibrium. And if we have a translation equilibrium, which means that this rod will not move ahead or downwards. In this case, the rod will move downwards, right? But in this case, what will happen is that, let's say this is the center, then only you have translation equilibrium. So which means that this will not move any further, but this doesn't have a rotational equilibrium because this is going in the anti-clockwise and this is going again in the anti-clockwise. So it does not have a rotational equilibrium, which means that it will have a rotational motion only, right? So it will have a rotational motion only. So this is the example of a couple. This is a form of torque in which the body is not moving translationally, but it is moving only in, so only the rotational motion is there, right? In this fixed axis, so this object is rotating. So you have, oh, yeah, so you have this object and you are applying one force in this way, another force in this way. So it will rotate, right? So you have this one. So one force in this direction and this one on the white cap. So this is downward, this is upward. So it will rotate, right? It will rotate like this. So whenever you have these kind of forces, this one same magnitude, this one same magnitude. So this will rotate, right? So
Yes, sir.
this kind of force is called the couple, right? So whenever, yeah. So what is a couple? Let me write it in here. So you guys understood that it will only have a rotational motion, right?
Yes, sir.
What is a couple or a torque? This is an example of a torque, right? When two forces of equal magnitude are applied in the opposite direction, then those forces will create a rotational motion. So that kind of force is called couple. Okay, so you have seen this example in your daily life also. So let's say you are again giving you this same example you have seen in the NCRT textbook. So you have this bottle, right? And let's say these are the 2 points. So this is my thumb and this is my let's say pointer. So I am producing a couple, right? So this is creating a rotational motion. This is not moving in the upward or down. This is actually moving in the upward direction. But this is creating a couple, right? So
Yes,
this
sir.
is creating a rotational motion and then this is the, right? So this is the example of a couple. Okay. And with the rod also you guys have seen that. So yeah, that is whenever 2 forces are acting in the opposite direction and they have the equal magnitude. So those are called the couple forces. And they have different line of force also. So you can see that this one has a line of action in this direction. So this one has a line of action and this one has a different line of action. Both have a different line of action. Both are not on the same line of action, right? So if this force is acting downward, so then it will not move, right? Both has to be in different line of action. So this is called the line of force or line of action. So you guys please note down this part, right? And this part you guys have already noted it down, right? So
Yes,
please
sir.
note down this part and then note down about the summary. And in the meantime, let me check this. What is that? Yeah, whenever you guys have noted it down, and if you guys have any confusion, please let me know. Right. Yeah, I want to finish this inertia part. Let us finish that. So we will do 2 questions based on these equilibrium part, and yeah, then this would be because those are very important questions. That is given in the NCRT part.
Finish, sir.
Then please down this part. And importantly, both these forces have different line of action. Yeah, whenever you guys have noted it down,
Done, sir.
yes, everyone noted down.
Yes, sir.
Yes, so now let us talk about right, this, this topic comes under this of things. Right, so what is the use of these moment of force, moment of angle of momentum? So in the principle of momentum, moments we have this lever. So what is a lever, right? It is an ideal rod which has a negligible mass. Right? So this is an ideal rod and it has a negligible. And the point at which we pivot, so we rotate this rod, right? So the point at which we rotate this rod is called, so let's say this is point P. So this point is called the fulcrum. So what is the fulcrum? The point at which the lever is right. So rotated is called, or rotated or pivoted, right? Is called fulcrum. Okay. So what is the use of this lever? So you guys have seen the barriers, right? So in the barriers and in the children's park, you have these seesaw, right? So you have these seesaw and it has some fulcrum. So let's say some children is sitting here, some children is sitting here. So this moves, so this seesaw moves, right? So this uses the idea of the lever, right? So this is used, and then you have these in the car crossing or in the, so you have these barriers, right? So these barriers are placed and these are moved, right? Whenever this car is approaches and it has a ticket, so then this barrier is open up and then, yeah. So in these also you this these lever are used, right? So they have two forces acting in downwards, right? So let's say this is F1 and this is F, right? So this one is called so this one is called the loop. So you are loading in here something, some weight is loaded here, and then you are applying some effort in this part, right? So this F2 is called the effort. Okay. And this is the distance, let's say this is the load distance, and this distance D2 is called so let's say this is called the effort distance, right? So this is about the lever, and what is the use of lever? That you apply some effort, right? And then on the basis of this effort, you can just increase or decrease. So that is the idea of this lever, right? So there would be two kinds of equilibrium, right? This is a rigid body. So there would be two kinds of equilibrium on this rod. So let's say at this point, there would be some normal reaction, right? So let's say this is the normal reaction R, right? So we have we have this lever, and this is the normal reaction, and this is the two forces, right? And this is the point with at which we are measuring the rotation. So this is the fulcrum. This distance is d1, and this distance is d2. So this is our line of force, right? This is our line of force. Okay, so first we have to apply the translation equilibrium, right? So from translation equilibrium, what would be the condition? From translational equilibrium, whatever is the upward force, that would be equal to the downward force, right?
Yes, sir.
So R would be equal to F1 plus F, right? Am I correct?
Yes, sir.
So this is so R minus F1 minus F2. This is the first condition. This will not be used, but and from the so there is another equilibrium, right? What is that equilibrium? Rotational equilibrium. And axis of rotation is this point, fulcrum, right? So from here we are rotating this lever. So from that, how many torques do we have? This is the force.
One,
This is the force. This
two,
is the
sorry.
yeah, and this R is also there, but it is on the axis. So its torque would be zero, right? So we have two torques, and they are balancing each other. So this one is there, and this one is there, right? So they are balancing. So F1 would be, and let me write it as tau 1, right? Tau 1 would be equal to tau 2. So you guys know that what is the torque? What is the magnitude of the torque? So whatever is the
The total
perpendicular,
torque,
yeah, what is the torque for this point? What is the torque? Yes. So torque is R perpendicular into F, right? This is the magnitude of torque, right? Right, everyone.
yes, sir.
Yes.
So what is the perpendicular distance from this point to this force? So is this the perpendicular distance? Is this the perpendicular distance? What is the perpendicular distance? This is the line of force, right? And what is the perpendicular distance from this point? D1, right?
Sir, only P, right?
B, I'm talking about the distance between this line of force and this point of observation, axis of rotation.
Okay, sir.
So tau is R perpendicular into F, right? Tau is R cross F, and this we have seen that this is R perpendicular into F, right? So this is the perpendicular distance D1, so D1 and F1. Similarly, this is D2 and F. So if we take this in this side, so this is D1 F1 minus D2 F2. This is equal to 0. So there is a way of writing this one that you guys also can calculate the direction. So this is D1, and we are going in the clockwise or anti-clockwise direction. This is
Sir, for
clockwise,
F1, we are going anti-clockwise.
anti-clockwise. So if you curl your finger, what is the direction you are getting? Inwards or outwards?
Inwards,
Inwards.
outwards,
So you have said two answers. Which one? Inward or out?
out,
Outward.
most probably.
Probably there is just Still confusion. Yes, Rishita, Amna, and Anna. What about you? What do you guys think? If you call your fingers in the anti-clockwise direction, so what is put your curly fingers in the direction of anti, right? What is the direction that you are putting? Upwards, outwards, or inwards? This
Out.
is this is the direction, right? This
The
is the direction.
inward.
Inwards.
So, inwards.
Inwards you are getting. How you are getting? So this is anti-clockwise, right?
Yeah.
So it is outwards,
Oh,
right?
yeah. Yeah. Yes, sir.
Right. So this is outwards. And if you are going inwards, so let's say if this is clockwise, right? This is your clock. So if you are going clockwise, so then this is clockwise. So this is how we write sign. So whenever we are going anti-clockwise, so that would be positive. You just check it uh, with the Maxwell's number, right? And whenever you are getting you are going clockwise, so then that would be right. So either we can write this one or we can write this. Is this clear? So in the next question, when I will do that, so I will write in this way. So is this part clear? Whenever we are going anti-clockwise, then tau is positive. Whenever we are going clockwise, then tau is clear, everyone.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so yeah, so we have this condition, right? So we got, let's say this is second equation, and this is the first equation. So from the first equation, what did we get? So D1 F1 equals to D2 F2, right? So which means that F1 by F2, this is equal to D2 by D1. So this F1 by F2 is called the mechanical advantage. Right. So what is the general idea in the lever? What is the general idea in the lever? That we want to reduce the effort, right? So this part is the effort part. So we have this lever condition, and in that we have this D1, which is the load distance, right? And we have this F1, which is the load. We have this D2, which is the effort distance. And then this is the F2, which is the effort. So the idea is that we want to reduce the effort, right? We want to apply the minimum effort that so that we can get the maximum load, right? Are you guys understanding? So we have this seesaw. We have this seesaw in the park, and we want to apply the minimum effort that so that this child can go higher, right? Are you guys
Yes, sir.
understanding? Yeah. So then what do we do? So we increase this D2 distance, right? So
Yes, sir.
if we increase this D2 distance, so if D2 is greater than D1, so we have increased this D2, right? D1 is small. Then what will happen? So D2 by D1 would be how much? If I take this in the left hand side, D2 by D1 would be how much?
0.
This is in the denominator. Okay, so let's say this is 3x equals to y. If I take y in this side, so what will be here?
1.
1. So this would be 1, right? Why this would be 0? If I write d2 minus d1, right, then it would be 0. Right, sir?
Yes, sir.
So my D2, my effort distance is greater than the load distance. Then this part is greater than 1, right? So if this is the condition, then what will happen to the mechanical advantage? Then mechanical advantage would obviously be greater than 1, and F1 is F1 by F. What would be this? What would be this, guys? D2 by D1 is greater than 1. So F1 by F2, if you put this value,
Smaller than 1.
greater than 1, right? We are putting the value of
Eh,
D2 by D1.
okay.
So your F1 would be greater than F, right? Which means that if you apply a small effort, so your load is greater than your effort. So this is what you want, right? In the lever, this is what you want, right? You
Yes,
want
sir.
a minimum effort so that you get a greater lift. So whenever you are in the park, right, and you are taking your younger sisters or brothers, then you keep a longer distance in the seesaw, and then you'll have to apply minimum effort, right? This is the idea, guys. And then you can increase the mechanical advantage. So to increase the mechanical advantage, what do we do? To increase the mechanical advantage, we increase, right? So D2 should be greater than D1. So this is the criteria for mechanical advantage. Any doubt in this part, guys? Any question?
No,
No,
sir.
sir.
Yeah, then please note it down and please note down. And then we'll do two questions, and then I will talk about this. What is that? So, center of gravity and then inertia. So we'll do the topic. But before we do those two questions, so if we do that problem, then then we'll understand about these rotational and translational. Hopefully, in the next class, this chapter would be over, and then we will do this gravitational part. So most of the part we have done in work energy and power. So we have just used this potential energy, gravitational potential, those things we done, right? We have to use just those conditions. And always remember, we have to apply both at the equilibrium, right? Translation
Yes, sir.
equilibrium and rotational. Whenever we have a rigid body, then we'll have to apply both the conditions. And to apply those, we have find an axis of fulcrum. In the case of liver, we found the fulcrum, right? So in other cases, we'll find the pivot point.
Finish, sir.
Then please Yes, whenever you guys have noted it down.
Finish, sir.
So you have seen the example of liver in many cases, right? Let's say whenever the driver or someone changes the tire of the car, then he applies some river, right, beneath the car, and then he applies some effort, and then the car is pulled up, right? So you can
Yes,
see
sir.
that by the idea of lever, he cannot lift the car, right? So the person cannot lift the car, but using the idea of lever, he can lift the car. This idea is very
Finish, sir.
everyone
Yes, sir. Yes.
done.
Yes, sir.
So let us do two question, and then we'll understand about this equilibrium part very close. These questions are very important, and these are both NCERT problems. Right? So in the first, let me bring the question.
Sir, I'll be joining from another device, sir.
Yes,
I'll
yes,
just leave this
yeah,
device.
yes, of course, yes. Sixth chapter. So always remember whenever we are doing rigid body, right? So then we have to apply two equilibrium, right? Translation, rotation. So
Yes, sir.
and torque is perpendicular distance with the line of force, line of action, and the to the force, right? So distance into the force, that is the torque. Now it is there. And can you guys tell me what is the dimension of what would be the dimension of the torque? Dimension of torque, how much would be that? So torque is R into F, right? So this is dimension of R is distance. So this is meter, and this is kg meter per second square. Force is mass into acceleration, right? Mass is kg, acceleration is meter per second square. So this is
Yes, sir.
kg. This is kg meter square per second square. So the dimension of torque would be m L square t minus 2, But can you guys identify this dimension? What is the dimension? So is this matching with other dimension?
Yes, sir.
Yeah. What is it with which it is matching?
Force.
Force has LT ML and
Sir, work.
T minus 2. This is force, right? Okay, so Akib is saying work, right? Work is force into distance, right? So that
Yes,
Energy.
is,
sir.
yeah, energy also. So energy is mgh, right? Or half mv square. So work has or energy. These have also the dimension of 2 minus. But this is a totally different physical concept, and this one is different, right? Because work energy are different things. Work energy can be put in the same. They have the same physical, but torque is totally different quantity, right? But they have the same damage, right? So that may be the drawback of this damage, right? Because two physical quantity can have the same damage, right? Oh, so now let us go back to this question. Which way there? This is equation. Okay, so a metal part, right? We have a metal part, and this is 70 centimeter long. So we have a metal bar, and now see that this is not a lever, right? Why this is not a lever? Because it has a mass, right? 4 kg. So that is why this is not a lever. So a metal bar, this is 70 centimeter long, right? And the center of mass would be the geometrical center, right? So all the masses would be concentrated in here. This would be the weight of this metal bar, right? And then, so in mass supported on two knife edges, right? Placed 10 centimeter from each end. So this is one end, right? This is second end. So 10 centimeter from this end, there is this knife edge, right? And 10 centimeter from here, there is this knife edge, right? And this is placed. So this surface is touching. So there would be a normal reaction in this direction, and if we write it with different, there would be there would be a normal reaction in this direction and a normal reaction in this direction, right? So how much would be this distance? Can you guys tell me how much is this distance? This distance is we know. So 70, so that is 35, right? How much is this distance?
So 70 minus 35?
No, 70 is total distance. 75 by what did you say?
35.
35 is this distance. From here to here, this is 35, right? Center.
Yes, sir.
And this knife edge position. So this is 10 centimeter from here, right? So this would be 25. Clear?
Okay, sir.
Because this total is 35, so this would be 25. Is this clear, everyone? Similarly, this is 25, right? And this is 10. So is this point clear?
Yes, sir.
Yes, sir.
And there is this, so a 6 kg load is suspended at 30 centimeter from one, right? So 6 kg load is suspended at this point. From here to here, this is 30 centimeters. So from here to here, that would be how much? There is this load which is placed, right? So this is the load, WL. And this is placed from here, which is 30 centimeters. So this is how much, guys? 5. Total is 35, so this is 5. Clear?
5 centimeters.
Yeah. And we will assume that this is the axis of rotation. So this is the pivot point, right? This is the pivot point. So then this reaction will move in this direction, right? Now we can write all the things. So the load mass is, yeah, so what do we know? We know that load mass is 6 kg and rod mass is, this is 4 kg, right? So mass of food is, right? Okay. So now we have every information and now let us write it clear. So it goes. What are the forces that we have? So this is our weight, right? Which is how much? So this is
4 kg.
yeah, this is 4 kg. So weight would be 40 Newton, right? Let me write it here as tau. What we know that how much is tau, right? And then we have this load, which is 60 Newton. And then we have this reaction 1, and then we have this reaction as this is R1 and R2, right? And then this is rotating in this direction, this is rotating in this direction, and this is rotating in this direction. Clear, everyone?
Yes, sir.
So this distance
Yes.
is, yeah, this distance is 25. This distance is 25. This distance is 5. And we are assuming that this is the axis of rotation. Okay. So applying the first criteria is applying translation equilibrium, right? So one force is upward, this is upward, and these two are downward. So we can write that R1 plus R2, this is downward, so minus W minus WL, this is 0. Is this part clear?
Yes, sir.
Yeah. Whatever is going in the opposite direction, that is negative. So downward direction is negative. And we can also understand this in this way, that R1 plus R2, this would be equal to W plus WL. This is also correct. And then we can write it in the left hand side. So this would be the first equation. Is this part clear, everyone?
Yes,
Yes,
sir.
sir.
So W is how much? Weight is 4 kg. So that is mg, right? So this is 4 into 10. So this is 40. And load is how much? 6 into G. So this is 60. Understood, everyone?
Yes, sir.
So,
Yes,
R1
sir.
plus R2 is 40 minus 60. So this is R1 plus R2 minus 100 equals to 0. Yeah, and the question is that we have to find out what is R1 and R? These are the two things that we have to find. This equation is R1 plus R2 equals to 100. So this is the first equation, right? This is a linear equation. So now we have got the one equation. And the other equation, where do we get, so where will we get the other equation, guys?
From applying rotational equilibrium.
Yes, absolutely right. So we have to apply the rotational, right? So let us write the rotational equilibrium. Again, let us draw the diagram here so that we can easily write it. One reaction is this way, and this is the point of rotation that we are taking, right? So one is in this way. This is 25, and then this is 25. This is R2. This is R1, and then this one. This is W. This one we will not count because this is in the line of the uh, rotation, right? So this is the rotational axis. So here the rotational torque would be 0, right?
Yes, sir.
Okay, so now you guys, Akib, you tell me that what would be, so Rishita, you also, and then Elham, then you guys tell me what would be the rotational equilibrium, right? So applying the rotational equilibrium. What would be that? Yes. So there are three torques, right? One, two, three torques. There are three torques. So for this one is clockwise or anti-clockwise?
And clockwise.
Clockwise, so this would be positive or negative?
Negative.
Negative. So what would be the, let me write it as
Minus 25.
yeah, so tau 1 plus tau 2 plus tau 3, this is 0, right? So tau 1 is minus 25 and this is
Plus
the
25 will be R2.
what is this is the distance, right? And there is this also T into force. What is the force?
Force.
This
Sir,
is
but
the
R1 and R2, they are given total, not separately. Then how can we?
no, so forget about this part. What is the force which is acting at this point? So let's say you have this force which is acting. Let's say F, and the distance is D. So what would be the torque? FD, right? Or D into F.
Yes, sir.
So minus 25 into,
25.
so 25 is the distance. What is the,
Sir, R1 is not given.
yeah, R1, so you
So
can say
R1.
R1, right? So R1 is the,
Okay.
right? Because we have to find out R1. Yeah. Yes, everyone understood.
Yes, sir.
Yes, sir.
Okay. And then tell me about this R2. So what would be this one? This is clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise.
Anti-clockwise. So this would be positive or negative?
Positive.
Positive.
So what would be the torque?
Plus 25 R2.
25 R2. Good. And the last one, right? This one is clockwise or anti-clockwise?
Anti-clockwise.
So what would be the, yeah, this distance, right? So what would be
5
this?
centimeters. Plus 5 W2.
Right. So this is good. Good, everyone. So this is from the rotational part, right? So this would be how much? Minus 25 R1 plus 25 R2 plus 5 and WL we know. How much was that? That
6
was
kg.
60, right?
60 Newton.
That was right. So 60. this is 0. This is minus 25 R1, and this is 25 R2 plus 6 5. Well, let us take, yeah, so this is 5, and this is 5 into 12. Okay, so what I will do is that I will take minus 25 common. So this would be R1, this would be R2, and minus of 12. Here, everyone.
Yes, sir.
So this
Yes,
20,
sir.
this both the minus and 25 goes in the right hand side, and this is this equation. So this becomes this, and R1 minus
R1
R2.
minus R2 equals to 12.
So now we have got the two equations, right? One equation we got from the translation equilibrium, and this one for the rotation equilibrium. So using the first equation, right? Then this would be, this was 100, I guess, right? So
Yes, sir.
we add these two, or we can subtract also. Let us add these two. So we add these two. So this is 2R1, this is cancelled, and this is 112. So R1 is 112 by 2. So this is 56 Newton, right? And then we have this, yeah, and then we have, what was the other part? So R1 minus R2 is 12. So this is 56 minus R2 is 12. So R2 is 56 minus 12, so 40. So this is the R. Remember, I have taken G to be 10 meter per second square, right? So if I take G equal to 9.8, then the answer would be different. So yeah, we can take these, or we can take this. If this is mentioned that we have to take G equal to 9.8, then we have to take this one. But if it is not mentioned, then we can take either 10 or either 9. Any doubt in
Yes,
this?
sir.
Yeah, any doubt in this question, guys?
No, sir.
Okay, so then please note down this question, right? So this image was the crucial information, and if we got this image, then the rest part is. Whenever you guys want me to scroll down, please. Match is also good. Right.
Finished, sir.
Whenever you guys have finished, you can please,
Sir, can you scroll down?
yes, whenever you guys have.
Done, sir.
Done. Okay, so everyone noted.
Yes, sir.
Let's do one more question. Now you guys understood about this rotational and translation, right? Laws of motion in the fourth chapter, we only talked about the translation. Okay, so the next question is again here, right? You have a ladder, right? And it is kept on this wall. So you have this ladder which is kept like this, right? And this wall is frictionless. This is a 3 meter long ladder. This one is 3 meter long, right? And weighing 20 kg, right? So again, the center of mass would be in here. So this is where the weight would be, right? So let's say this is the weight, and wall is frictionless. right? So if you place the ladder in this way, so this will slip in this direction, right?
Yes, sir.
But this surface is having some friction. So to save this from slipping, the surface it will apply the frictional force in this direction, right?
Yes, sir.
Okay, so this one is there, and its feet rest on the floor 1 meter from the wall. So let's say uh, this feet is, so this is the wall, and this feet. So this is 1 meter, right? This is 1 meter, which is given, and what else is given? Find the reaction forces of the wall and right. So here we have this wall and this surface. So we have this first reaction surface perpendicular to this wall, right? So this is one, and then we have this normal reaction at this point. So this is in here, right? So this is the normal reaction, and this is the normal reaction at this point. And this friction and this normal reaction will have resultant, right? So let's say this is the result. Okay. So we have to find out this F1, and we have to find out this F. These are the things that we have to find. Okay. So did you guys understand the diagram?
Yes, sir.
Yeah. So this is 1 meter and this is 3 meters. So how much would be this? So we have to find out F1 and F2, right? This is 3 meters, this is 1 meter, so this would be 3 square minus 1 square. So this
Root
is
8.
root 8, which is 2, right? So all the distances are right. Okay, and yeah, this is the point. So let's say this is A point, this is B, and this is and we know all the forces. So if we apply the translation equilibrium, right? So how many forces are in this direction? How many forces are in this direction? How many forces are in upward direction? How many forces are downward direction? So there are two translation equilibrium, right? Left to right,
Yes, sir.
up and down, right? So if we apply the, and what is the weight of this ladder? So this mass of ladder is 20 kg. So weight would be how much? 20 into 10, which is 200, right? 200. Okay, so what we can calculate? So we have this force, right? This is the force, and then we have this force, and then we have this force. This is the frictional force, and this is the normal reaction, and this is the resultant of that. So calculate that, right? Because this is N, this is F. So what would be the resultant of N and F? That would be, let's say F2, that would be F square plus N square. Is that correct?
Yes, sir.
Right? Because these are perpendicular. So what is the resultant of two forces? Resultant is F1 square plus F2 square plus 2 F1 F2 cos of theta. Theta between them is 90 degrees. So this is 90, this is cancelled, so this would be simply this one. Right. So now writing the translation. This one is right, this one is left. So F1 equal to F. Here, guys,
Yes, sir.
and this one is up, this one is down. So N equal to W, right? And W we know that is 200. So N we have calculated, right? So uh, this is what horizontal part, and this is the vertical part. This is vertical equilibrium. This is horizontal equilibrium. Now we have to apply the translation equilibrium, rotational equilibrium, right? Rotational equilibrium. So we can apply the equilibrium in different cases, but we can choose this point as the point of rotation, or we can choose this point, or we can choose this point. So if we choose this point, then rotation due to this force and this force will cancel, right? This will be zero if we are choosing this point,
Yes, sir.
right? So then what would be, so if we choose this point as the rotational point, right? So we have this point, so this is the line of force, and we have this force, right? So this one is in this direction, this was in this direction, right? This F1 is clockwise or anti-clockwise?
Anti-clockwise.
So F1 is anti-clockwise, so this is positive. W,
Positive.
yeah, W is
And W is negative.
negative, right? So you guys tell me that this is 2 root 2, right? Meter, and this is 1 meter, right? And this is how much? So this is W. So we have to write for the case of W and for the case of F1 from this point. So what would be the torque? Tau 1 plus tau 2 would be 0. What would be the torque, guys? Yes.
Sir, F1,
Yeah, F1
F.
into how much?
F1 is F, right?
Yeah, F1 is F, right? Absolutely correct. But yeah, F1,
Into
F,
3.
F1 into 3.
Yeah, it
This,
is 3 meter, right?
okay, so what is the line of force here? You tell me. What is the line of force?
Line of force is
F1.
the line above W.
This is the line of force of F, right? This is the line of action of F1.
Yes, sir.
And what is the perpendicular distance from this point? E or something else? Yes.
Sir, either it is N or 2 root 2.
N is a force, right? We have to
So
calculate
2
the
root 2.
tool. Yes, everyone, is this part clear?
Yes, sir.
And minus of tau 2. So tau 2 is this is negative. So W into how much? This is in the middle, right? So W into how much?
1.
1 or this is right. How
Sir,
much?
it will be perpendicular, right?
Yeah. So we have to find out. This is now. This is the point, right? This is the line of force, and
Yes,
we
sir.
are calculating from this distance. So this is the distance, right? This is how much? 1.
Okay, I took total.
Yeah. So total is 1. So this would be how much? This is the middle point, right? 1 by 2. Clear, everyone?
Yes, sir.
Yes, sir.
Now let us F1 2 root 2 equal to W we have calculated 200, right? So 200 by 2. So F1 is 200 by 2 into 2. This is 100. This is 50. So this is root 2 divided by root 2. So 50 root 2 by 2. This is 25. Right? So 25 into 1.41. This is how much? 70. So and 35. This is 35. Right? So F1 is 35 Newton, which means that yes, F1 we wanted to calculate. Right? The question was F. So and F2 we can also calculate. So F2 would be how much? F1 is 35, so that is equal to F, right? And we know that F2 is root of FF square plus W square. So this would be 35 square plus 200 square. So that would be something like this. 199 points. Right? So how much we got for 199? This would be 1. But they are using G to be 9.8, so our answer may be different. So you guys please calculate and check what it is, right? Because they are getting F1 to be 34.6 because they have used G to be 9.8, right? So if you use G10, then this would be 10. So any question in this, any doubt in this question, guys?
No, sir.
No, sir.
Please note it down. Please note it down. And this part is very crucial. So to identify the perpendicular distance, we always write the line of action. So from line of action, we calculate the perpendicular. If we are clear on that, then questions will
Sir, is there any class assessment today?
be. Yeah, there is the class, so you can check. Please check if there is this active test or not. And if there is this active test, then please, after this class, then please take that test. Right. But before, please note it down.
No, sir, it's not there.
It's not there.
No, sir.
Why this is happening? Because they are saying that. Okay, let me talk to the. Okay, who got disconnected?
Finished, sir.
Ilham got
Done, sir.
where did Ilham go? Yes, whenever you guys have noted
Don't see.
then yeah, so you guys understood that why this perpendicular distance was 2 root 2, right? Because this distance was 2 root 2, this was f1, and from here we were calculating, so this was f1, and this distance was 2, right? From there we got. Yes, whenever you guys have noted it down, please.
Finished, sir.
And Akib, you please also check that whether the test is active, right?
Yes, sir. Please give me 2 minutes.
Yes. Yes.